Hi everyone, today I'm going to present a thorough introduction about governing equations of fluid dynamics in mesoscopic and macroscopic scales from Lattice Boltzmann Method to Navier-Stokes Equations. Before I present the fluid dynamics governing equations, let's first answer the question, what is a fluid? A fluid is a substance that cannot resist a shear, as shown here schematically for a fluid particle. Any shear stress applied to a fluid, no matter how small, will result in motion of that fluid. The fluid moves and deforms continuously as long as the shear stress is applied. We can also say that the fluid at rest must be in a state of zero shear stress, a state often called the hydrostatic stress condition in structural analysis. Generally, a fluid flow can be described using three different scales: microscopic scale, mesoscopic scale, and macroscopic scale as shown here. Microscopic scale. In the macroscopic scale, as we can see here, the medium is considered as space containing particles like the substance made of molecules. Molecular dynamic simulation can be carried out by applying the Newton's equation of motion to describe the motion of each individual particle. Thus, in the macroscopic nature, methods describe deterministically the motion of individual fluid particles. However, performing such a simulation is expensive in terms of time and memory of computer. Thus, a simulation domain is often limited in a very small space, as we can see here, which is not feasible for most of industrial applications. Mesoscopic scale. This is a well-studied scale in terms of the description of gas flow. Generally, knowledge about the mesoscopic view of fluid flow fills the gap between the microscopic and macroscopic scales. As can be inferred from this figure, this scale is such that the number of particles becomes larger and it is more convenient to average all particle properties over a certain volume. The main assumption is that the behavior of a single particle in microscopic scale cannot describe macroscopic phenomena of fluids. However, a characteristic of a group of particles might be important in the macroscopic scale. Macroscopic scale. In this case, it is assumed that the fluid is a continuum and it is regardless that the fluid is made of molecules and atoms. In the macroscopic scale, physical variables of a continuous flow field such as density, velocity, pressure, and temperature are considered. Fluids are considered continuum fields and fluid flows are described by continuum models. In the continuum model, the spatial distribution of physical variables with regards to others under the physical laws such as mass and momentum conservations are expressed by a set of partial differential equations such as the Navier-Stokes and continuity equations. Now let's discuss the descriptions of fluid flow motions in mesoscopic and macroscopic scales in more detail. Mesoscopic scale, Lattice Boltzmann Method. For the description of the fluid flow motions at a mesoscopic scale, Lattice Boltzmann Method (LBM) is usually used. In this method, the governing equations of fluid flow motions are derived based on the collision and propagation of particles at a mesoscopic scale. In this regard, a density distribution function f as a function of x, u, and t is adopted that represents the number of particles per unit volume having velocity u within the volume centered at x and at time t. In this method, the space is discretized into a number of regular Cartesian lattices as shown here. Each lattice is specified as d, d, q, q, where lowercase d indicates the dimension and lowercase q shows the set of streaming directions. The most common lattices are the D2Q9 illustrated in this figure and the D3 Q19 model with 2 dimension here with 9 streaming directions and 3 dimension with 19 streaming directions. Particles are located on the nodes of the lattice as shown here and have several permitted streaming directions. EI, as you can see here, indicates the velocity vector of each fluid particle located on the nodes of the lattice. For instance, in this case we have E0, 0, 0, E1, 1, 0, E2, 0, 1, E3, minus 1, 0, E4, 0, minus 1, E5, 1, 1, E6, minus 1, 1, E7, minus 1, minus 1, E8, 1, minus 1. Thus, the Lattice Boltzmann method treats fluid as particles that stream along given directions, which are called lattice links, and collide at lattice sites. The Lattice Boltzmann equation, as defined here, is applied to each of these fluid particles at the lattice nodes. F here is a discrete distribution function that governs the propagation and collision of particles. This equation describes statistics of the system by distribution functions f, i.e. number of particles at time t, which have position and velocity between x plus dx and e plus de respectively. The discretized form of this equation is written as shown here. The left-hand side of this equation represents the propagation step or streaming that is associated with the advection term in the fluid mechanics equations. During the streaming step, the distribution functions Fi are propagated to the neighboring nodes of the lattice in the permitted I directions following this equation. The term on the right-hand side, which is the collision term, can be defined by different operators. The simplest one is the BGK collision operator, named from Batnager, Gross, and Crook, as is shown here, where the distribution function is close to a local equilibrium and relaxes to this value with some characteristic time tau. The local equilibrium FIEQ can be derived from the Maxwell-Boltzmann velocity distribution from statistical mechanics by assuming ideal gas law, the isothermal ideal gas pressure relation, and finally a low Mach number, allowing us to truncate the Taylor expansion to the second order without loss of information. We arrive at the following equation. Here Cs is the speed of sound in lattice units, and Wi are weights associated with the lattice. Note that the Lattice Boltzmann method can be based on diverse possible lattice configurations, as mentioned earlier in this video, but not all of them are appropriate. The different lattice configurations must meet certain requirements to give sufficiently isotropic behavior to recover the Navier-Stokes equation in the macroscopic scale. These requirements are defined as follows based on the Wi. For different lattice configurations, we have to define its d-dimensionality and the number of lattice vectors q, d, d, q, q nomenclature. The most common lattice configurations are the D2Q9 and D3Q19, as mentioned earlier and shown here, where the speed of sound Cs have the same value of 1 over root square 3. As an example, we have the D2Q9 lattice in the figure, with these characteristics for the weights associated with the lattice. Based on the conditions given here, we have these equations for the weights associated with the lattice. Thus, we're going to have the following values for weights Ws, which are the weights associated with the lattice. Here we can see the values of W for each of these lattice configurations. The macroscopic values of density ρ and velocity u are obtained from the following equations. The fluid kinematic viscosity nu is usually fixed based on the collision relaxation time tau, the lattice space delta, and the time step delta t, and is given as shown here. To consider the turbulence effect, it is common to add a turbulence model based on RANS or LES to the Lattice Boltzmann model. At each step, the Lattice Boltzmann method provides distribution functions f on the full domain, and macroscopic quantities associated with each node are then calculated. Note that as the most of the operations on the lattice nodes are independent from their neighbors, at least during the collision phase, thus parallelization can be easily implemented. The Lattice Boltzmann method offers a computational cost which is normally less than those for finite volume and finite element methods. The advantages of this method is first, highly parallelizable, two, ability to handle the complex boundaries. However, there are some disadvantages as are shown here. It is subject to artificial compressibility when solving the incompressible equations. 2, it is not well established for turbulent flows, especially for large Reynolds numbers. 3, simulation of moving geometries and 6 degree of freedom motions, as well as dynamic FSI, are not yet possible. Macroscopic scale. In this case, the fluid is assumed to be a continuum, which simply means that its properties vary so smoothly that differential calculus can be used to analyze the substance. Eulerian and Lagrangian descriptions. In a given flow situation, the determination of the properties of the fluid as a function of position and time is considered to be the solution to the problem. In almost all cases, the emphasis is on the space-time description of the fluid properties. One rarely keeps track of the actual fate of the specific fluid particles. The first view, appropriate to fluid mechanics, is concerned with the field of flow and it is called the Eulerian method of description. In the Eulerian method, we compute the pressure field P as a function of x, y, z, and t, or velocity field V as a function of x, y, z, t of the fluid flow, not the pressure changes P as a function of t, or velocity changes V as a function of t that a particle experiences as it moves through the field. The second method, which follows an individual particle moving through the flow, is called the Lagrangian description. The Lagrangian approach is more appropriate to solid mechanics. Fluid dynamic measurements are also suited to the Eulerian system. For example, when a pressure probe is introduced into a laboratory flow, it is fixed at a specific position, x, y, z. Its output thus contributes to the description of the Eulerian pressure field, P as a function of x, y, z, and t. The velocity field. Determining the velocity field of a fluid flow, V as a function of x, y, z, and t, is often equal to solving a flow problem, since other properties follow directly from the velocity field. In general, velocity is a vector function of position and time, and thus has 3 components, u, v, and w, each a scalar field in itself, as we can see here. No slip condition. In a viscous fluid, when the flow is bounded by a solid surface, molecular interactions cause the fluid in contact with the surface to seek momentum and energy equilibrium with that surface. Thus, all fluids at a point of contact with a solid take on the velocity of that surface as shown here. This is called the no-slip boundary condition, and it serves as boundary conditions for analysis of fluid flow past a solid surface. The no-slip condition is applied only to viscous flows. In case of inviscid flows, the flow is allowed to slip past the surface but not to permeate through the surface, as we can see here. Additionally, the tangential velocity Vt is allowed to be independent of the wall. The analysis for inviscid flows is much simpler, but the flow patterns are highly idealized. The acceleration field. The acceleration vector, which is defined as the time derivative of the velocity vector, occurs in Newton's law for a fluid and thus is very important. Note that the final result for acceleration is nonlinear and quite complicated. Here, first the formula is presented as shown here. The last three terms in this equation are nonlinear products and greatly complicate the analysis of general fluid motions, especially viscous flows. The equations governing the fluid flow motions in continuum mechanics can be obtained by applying the basic conservation laws to an infinitesimally small control volume, or alternatively to an infinitesimal fluid system. The Cartesian vector form of a velocity field for a fluid flow can be written as follows. This is the most important variable in fluid mechanics. Knowledge of the velocity vector field is nearly equivalent to solving a fluid flow problem. The coordinates are fixed in space and we observe the fluid as it passes by. Thus, this is the Eulerian frame of reference as opposed to the Lagrangian frame, which follows the moving position of individual particles. To obtain the system of equations describing the flow motion, the acceleration vector field must be calculated. So now let's see how we can calculate the acceleration vector from the velocity vector. Thus, the total time derivative of the velocity vector is written as shown here. Since each scalar component u, v, w is a function of four variables x, y, z, and t, we use the chain rule to obtain each scalar time derivative. For instance, for the u component, we have this equation. By definition, we have dx over dt equals u, dy over dt equals v, dz over dt equals w. Thus, the acceleration components in x, y, and z directions are written as follows. Thus, the acceleration vector can be written as follows. This term, the partial derivative of velocity with respect to time, is called the local acceleration, which vanishes if the flow is steady, that is, independent of time. And the three terms in parentheses are called the convective acceleration, which rise when the particle moves through regions of spatially varying velocity. Note that our use of the compact dot product involving v, the velocity vector, and the gradient operator nabla, where nabla is presented here. The total time derivative sometimes is also called the substantial or material derivative. The use of this type of derivative is indispensable, especially when the variable under consideration changes both in time and space. Mass conservation equation. Conservation of mass, often called the continuity relation, states that the fluid mass cannot change. This concept here is applied to a very small control volume. All the basic differential equations can be derived by considering either an elemental control volume or an elemental system. An infinitesimal fixed control volume, dx, dy, dz, as shown in this figure is chosen. The flow through each side of the element is approximately one-dimensional, and so the appropriate mass conservation relation to use here is presented in this equation. Due to the smallness of the element, the volume integral simply reduces to a differential term, as we can see here. The mass flow terms occur on all 6 faces, 3 inlets and 3 outlets. Based on this figure, the continuum concept states that for mass conservation, if rho u is known on the left face, the value of this product on the right face is obtained using this relation. The same relations are also applicable to y and z directions as shown in this figure. Introducing these terms into this equation gives this relation. The element volume, which is dx, dy, dz, cancels out of all terms, leaving a partial differential equation involving the derivatives of density and velocity. This is the desired result, conservation of mass for an infinitesimal control volume. It is often called the equation of continuity because it requires no assumptions except that the density and velocity are continuum functions. That is, the flow may be either steady or unsteady, viscous or frictionless, compressible or incompressible. However, the equation does not allow for any source or singularities within the element. The vector gradient operator, as shown here, enables us to rewrite the equation of continuity in a more compact form as shown here. In this vector form, the equation is still quite general and can readily be converted to other coordinate systems, such as cylindrical coordinates. Steady compressible flow. If the flow is steady, all the properties are functions of space. Thus, the continuity equation reduces to this equation. Incompressible flow. Special case that leads to significant simplification is incompressible flow, where the density changes are negligible irrespective of the flow being steady or unsteady. In this case, the continuity equation is written as follows. Note that to determine if a flow is compressible or incompressible, all we need to do is to estimate the dimensionless Mach number as presented here. Here, v is the fluid flow velocity and c is the speed of sound in the fluid. A fluid flow can be assumed to be incompressible if Mach number is less than and equal to 0.3. For air at standard conditions, a flow can thus be considered incompressible if the velocity is less than about 100 meters per second. This encompasses a wide variety of air flows. Further, it is clear that almost all liquid flows are incompressible since flow velocities are small and the speed of sound is very large. Momentum equations. Here, an elemental volume is used to derive the momentum equations. The same elemental control volume used to obtain the continuity equation is used here. Based on the Newton's second law, we have this equation. Again, the element is so small that the volume integral simply reduces to a derivative term. The two last terms indicate the momentum fluxes which occur on all 6 faces, 3 inlets and 3 outlets as shown in this figure. In terms of each velocity component, the momentum fluxes on each face can be written as shown in this figure. Thus, based on this figure and this equation, the momentum equation becomes as follows. Note that this is a vector relation. A simplification occurs if we split up the term in brackets as shown here. The term in brackets on the right hand side is the equation of continuity, which is equal to 0. The long term in parentheses on the right hand side is the total acceleration of a particle as we can see here. Thus the momentum equation is thus the momentum equation is reduced to this equation. This equation points out that the net force F on the control volume must be of differential size and proportional to the element volume. These forces are of two types, body forces and surface forces. Body forces are due to external fields such as gravity that acts on the entire mass within the element. The gravity force on the differential mass within the control volume is calculated using this equation, where g is the vector of gravity acceleration. The surface forces are due to the stresses on the sides of the control volume surface. These stresses are the sum of hydrostatic pressure plus viscous stresses tau ij that arise from motion with velocity gradients as presented here. The subscript notation for stresses is given in this figure. Note that unlike velocity v, which is a three-component vector, stresses sigma ij and tau ij and strain rates epsilon ij are 9-component tensors and require two subscripts to define each component. Sigma ij indicates the stress in j direction on a face normal to I axis. It is not these stresses but the gradients or differences that cause a net force on the differential control volume. This can be seen in this figure, which shows the stresses in the x direction. For example, the surface force acting in the left direction on the left face, as shown here, balanced by the rightward force on the right face, leaving only the net rightward force on the right face. The same thing happens on the other four faces, so that the net surface force in the x direction is given by this equation, where dv equals dx, dy, dz is the volume of the element. In exactly similar manner, we can derive the y and z forces per unit volume on the control surface as presented here. Thus, based on these equations, an expression can be obtained for the net vector surface force as follows, where the viscous force has a total of 9 terms as presented here. This equation can also be expressed in divergence form, as we can see here, where tau ij is the viscous stress tensor acting on the element and is defined here. The surface force is thus the sum of the pressure gradient vector and the divergence of the viscous stress tensor as presented here. Therefore, the basic differential momentum equation for an infinitesimal element can be written as follows, where the acceleration is defined as shown here. Thus, the momentum equation can be expressed as follows in words: gravity force per unit volume plus pressure force per unit volume plus viscous force per unit volume equals density times acceleration. The momentum equation can be written as follows in terms of its components in x, y, and z directions. This is the differential momentum equation, and it is valid for any fluid in any general motion. Note that the last three convective terms on the right hand side of each component equation are nonlinear terms, which complicates the general mathematical analysis of the fluid flow. Inviscid flow, Euler's equation. The momentum equation, as shown here, is not ready to use until the viscous stresses are written in terms of velocity components. The simplest assumption is frictionless flow, where tau ij equals 0, for which the momentum equation reduces to this equation. This is Euler's equation for inviscid flow. Note that integrating the Euler's equation along a streamline yields the frictionless Bernoulli equation. Newtonian fluid, Navier-Stokes equations. For a Newtonian fluid, the viscous stresses are assumed to be proportional to the element strain rates and the coefficient of viscosity. For Newtonian incompressible fluid flows, the viscous stresses are written as shown here, where mu is the viscosity coefficient. Thus, using this equation for the viscous stresses in the momentum equation gives the differential momentum equation for a Newtonian fluid with constant density and viscosity as shown here. These are the incompressible flow Navier-Stokes equations named after Navier 1785 to 1836 and Stokes 1819 to 1903, who are credited with the derivation. They are second-order nonlinear partial differential equations and are quite formidable, but solutions have been found to a variety of interesting viscous flow problems. The Navier-Stokes equations have four unknowns, P, U, V, and W. They should be combined with the incompressible continuity relation, as we can see here, to form a system of four equations of four unknowns. Even though the Navier-Stokes equations have only a limited number of known analytical solutions, it is possible now to achieve approximate but realistic CFD results based on these equations for a wide variety of complex 2- and 3-dimensional viscous flows. Boundary conditions. The macroscopic scale governing equations are written as shown here. As mentioned earlier, here we have four unknowns, P, U, V, and W, and four equations. It can be demonstrated that this system of equations is well posed and can be solved analytically or numerically subject to the proper boundary conditions. As shown in this figure, the three most common types of boundaries encountered in fluid flow analysis are a solid wall, an inlet or outlet, and a liquid gas interface. First, for a solid impermeable wall, there is no slip, so the velocity of fluid is equal to the velocity of the solid surface. V of fluid equals to V of wall. Second, at any inlet or outlet section of the flow, the complete distribution of pressure and velocity must be known. Finally, the most complex conditions occurs at a liquid gas interface or free surface. If the interface profile is denoted by this equation, the linear boundary conditions at the interface can be written as shown here. And the pressure at the interface is equal to the atmospheric pressure as presented here. In case of the inviscid flows, there is no condition whatever on the tangential velocity component at the wall in inviscid flow. The tangential velocity will be part of the solution to an inviscid flow analysis. However, we let the flow slip parallel to the wall, but do not allow it to flow into the wall. The proper inviscid condition is that the normal velocities must match at any solid surface, as we can see here. The Navier-Stokes equations presented here are highly nonlinear, and therefore it is almost impossible to have analytical solutions for most of the fluid flows in practice. Analytical solutions exist only in a few simple cases where most of the terms in these equations become zero, such as the flow between a fixed and a moving plate and the flow between parallel plates due to pressure gradient as shown here. For this reason, several simplifying assumptions are normally applied to the Navier-Stokes equations to reduce the number of variables, such as the assumption of incompressible flow, irrotational flow, and inviscid flow. These assumptions result in more simplified governing equations. The stream function. For incompressible flows, the stream function, which is normally shown by psi, can be used to reduce the unknown variables to 1, which is the stream function. Using this function, which can be obtained by solving directly the momentum equation for this single variable, continuity equation is automatically satisfied. This function must be defined in such a manner that its gradients, as presented here, provide the flow velocity field. These equations satisfy the continuity equation for incompressible flows in 2 dimensions as shown here. The vorticity function, which is defined as the curl of the velocity vector, is related to the stream function as presented here. Taking the curl of the momentum equation and using this equation is obtained for psi. Here, nu is the kinematic viscosity. Note that although we have reduced the number of variables to 1, the resultant governing equation now contains 4th order derivatives. In other words, there will be 4 boundary conditions required on the stream function. Note that lines of constant psi are streamlines of the flow. In other words, if we find a given solution psi as a function of x, y, we can plot lines of constant psi to give the streamlines of the flow. Vorticity and irrotationality. One important assumption is the zero fluid angular velocity or irrotationality, which is a very useful simplification. It can be shown that angular velocity is associated with the curl of the local velocity vector. The differential relations for deformation of a fluid element can be derived based on this figure. 2 fluid lines AB and BC, initially perpendicular at time t, move and deform so that at time t plus dt they have slightly different lengths, I prime B prime and B prime C prime, and are slightly off the perpendicular by angles d alpha and d beta. Such deformation occurs kinematically because A, B, and C have slightly different velocities when the velocity field V has spatial gradients. All these differential changes in the motion of A, B, and C are shown in this figure. We define the angular velocity omega z about the z-axis as the average rate of counterclockwise turning of the 2 lines as shown here. Both the alpha and the beta are directly related to velocity derivatives in the limit of small dt. Thus, the angular velocity is defined in terms of the velocity gradient as shown here. In the same manner, it is possible to define the angular velocity about x and y-axis as shown here. Thus, the vector of angular velocity is half the vector of curl as we can see here. Here we can define the vorticity vector, which is twice the angular velocity vector as shown here. Therefore, the vorticity vector is a measure of the degree of local rotation in the fluid. Many flows have negligible or zero vorticity and are called irrotational, as is shown here mathematically. Frictionless irrotational flow. In this case, first, the momentum equation is reduced to the Euler's equation, as shown here, due to the lack of frictional forces. The irrotationality of the flow leads to the Bernoulli's equation for frictionless unsteady flow between any 2 points 1 and 2 along a streamline as shown here. For frictionless irrotational incompressible steady flows, this equation is reduced to this equation. This form of Bernoulli's equation under these assumptions is applicable between any 2 points within a fluid domain. However, note that in cases where the flow is rotational but still is steady, incompressible and frictionless, this equation will be only applicable along a streamline. Velocity potential. Combining irrotationality with frictionless assumption gives rise to a scalar function phi, similar and complementary to the stream function psi. As in irrotational flows, the curl of velocity is 0, as we can see here. Then the velocity vector v must be the gradient of a scalar function phi, as we can see here, where phi as a function of x, y, z, and t is called the velocity potential function. Knowledge of phi thus immediately gives the velocity components. And since we are assuming that the fluid is incompressible, substituting these velocity components into the continuity equation, we get the 3-dimensional Laplace equation in terms of velocity potential function. Therefore, the velocity potential must satisfy the Laplace equation. Thus, the complete mathematical problem of finding a velocity potential of irrotational fluid motion consists of the solution of the Laplace equation with relevant boundary conditions on the fluid. Note that phi, unlike the stream function psi, is fully three-dimensional and not limited to two coordinates. It reduces a velocity problem with three unknowns, u, v, and w, to a single unknown potential phi. The velocity potential also simplifies the unsteady Bernoulli's equation, because if phi exists, we have this equation. Thus, the Bernoulli's equation for inviscid unsteady irrotational flow can be written as we can see here. The typical boundary condition used in potential flow is the no velocity normal to the boundary at the body surface, as shown here, where n is perpendicular to body. Unlike the no slip condition in viscous flow, here there is no condition on the tangential surface velocity. Occasionally, the problem involves a free surface for which the boundary pressure is known and equal to the atmospheric pressure, as shown here. The Bernoulli's equation, as presented here, is used to obtain a relation between the velocity vector v and the elevation z of the free surface. For a steady flow, we have this equation. Note that this use of Laplace's equation with known values of the derivative of phi along the boundaries is much easier than a direct use of the fully viscous Navier-Stokes equations. The analysis of Laplace's equation is very well developed and is termed potential theory. Having found phi as a function of x, y, and z and t, from such an analysis, we then compute v, the velocity vector, by direct differentiation as shown here, after which we compute the pressure P from the Bernoulli's equation. The procedure is quite straightforward and many interesting, albeit idealized, results can be obtained. The potential flow theory describing the motion of a perfect fluid is mathematically very far developed and supplies in many cases a satisfactory description of real motions, for example the motion of surface waves. On the other hand, the theory of perfect fluids fails completely to account for the drag of a body. In this respect, it leads to the statement that a body which moves with a constant velocity through a fluid which extends to infinity experiences no drag, based on the D'Alembert's paradox. Note that the governing equation for fluid flows have been greatly simplified through the use of potential flow theory. In spite of that, when potential flow involves complicated geometries, the use of CFD methods is indispensable. This is the end of this video. I hope you found this video useful. Please let me know what you think about this video by leaving a comment in the comment section. Thank you for watching the video, and for further upcoming videos, please subscribe to this channel.